All right, this is our first meeting with Alex DePillis as a co-organizer, which I'm so delighted to have because I feel like um, we are in need of some more executive function in this team.
And he brings lots of energy and different perspectives. So we appreciate that,
Yes.
Alex. Thank
Great. You want executive function from somebody with ADHD, just for the record.
It's all right. It all makes magic soup.
Magic soup. Is that what you're cooking with? I think that's what they're cooking
That's
here.
what they're
with
cooking
biogas.
here, I think. Yes, we'll get to hear all about it shortly. All right. Is
So
there
we did have
anything?
an agenda, right?
Go ahead,
Piper, do you have an
Margaret.
agenda?
There was an agenda. Let's see if I can find it quickly.
I'll just drop what I have from Meredith in the chat.
Yeah, that's what I was looking for. Thank you. What date is this one? Yeah, was that the one she sent out on Friday, the 11th? I'm not finding my chat. Alex, is that the one that said meeting materials and had a couple of items? I'm not seeing the chat right now on Zoom for some reason.
And I tried to put it in the chat, but it's more than 1,000 characters apparently, or something.
Okay.
So I'm sort of confused. Doesn't look like 1,000 characters. Let me just try another way here. I'm going to scrub it of all formatting.
It starts with weatherized digester update, NREL EPA pilot. Is that the one? Because I'm not seeing the presentation that we've got.
Cold high digestion community of practice 16 meeting cold/high it begins.
Yeah, that's the email I have up, but it looks like a different agenda. All right, well, let me mess around with this while if you want to go ahead and we've got looks like a great presentation up on the screen.
Yes.
I want to introduce our speaker. Welcome. Alex, is that who made the contact?
Thank you everyone. Hi.
Yeah.
Alex DePillis, Vermont Agency of Agriculture. We can have a quick go around. How about who does what, especially for the benefit of our special guests, and that way they can introduce themselves as well. And I will not misrepresent anything about them. So how about I will introduce myself, and then I'll call on people ahead of time as to who's next. Why don't we just do that right now?
Okay.
I'll say
Thanks, Alex.
It's going to be me, then Wolfgang, and I'm just looking at my participant list, then Margaret, Emily, Piper, Ariana, hello, and then do you say Hajo or Hajo? And then Nate. So, and then Robin. Robin's on here too. So that'll be our order. I hope you heard your names. I'm just going to introduce myself and type up to prompt the next person as needed. I'm Alex DePillis with the Agency of Agriculture in Vermont. It's snowing out right now, and it's April, and I'm especially interested in this for farming applications. Yes, possibly for sanitation, but that's not really my thing. I'm really about farming, but this technology crosses over. So food waste, yes. Feces, not so much, not my thing. Anyhow, that's my interest. And Meredith, I left you off. Meredith is our host for IARPC, IRPIC. Do you want to say anything, Meredith?
Hi, just welcome. This meeting is being recorded and it will be posted to the IRPIC Collaborations website as well as our publicly available YouTube channel. So it's available for anyone who wants to view it. So you're welcome to send it out to people who you think might be interested that missed this meeting. And if you have any questions at any point, feel free to reach out to me.
So probably
let's see.
Hajo,
Yeah, go ahead.
you are next.
Well, I can just give a short introduction of who we are and what we do. So my name is Hajo, which is a nickname for Hans-Joachim. I'm from South Germany, now being a lecturer and researcher in Switzerland at the University of Applied Sciences in Wädenswil, which is close to Zurich, at Lake Zurich, as you'll see later on. We do a lot of teaching. We do a lot of applied research for Swiss industry, AD industry, composting industry, all around environmental biotechnology. That's what we also teach a lot. And Wolfgang is part of my group. And as we are applied university or a University of Applied Sciences, we are forced to do a lot of applied research projects. And this is one of them. So as I'm an AD expert, I got over the last years a lot of calls asking for AD system, very small micro AD systems for tiny house projects. And the dream was to fire up those energy needs they have in these tiny house community, which is growing also in Europe. But we never had measurement data. The only thing we saw is that there is a need to do some research, and we applied at the Swiss Energy Ministry for some funding, and we got the funding for this micro biogas project, as we call it, MIBAS, Microbiogas Switzerland. And so we set up a microbiogas plant coming from one of our former colleagues. She's working a lot in Northern and South Africa with this system. And the idea is to do a full year measurement tour here in Switzerland under real conditions. At the moment, we don't have snow. Snow is gone. We have spring in full swing now. It's getting warmer, almost 20 degrees. So the idea is to cover data for about a year and to give an insight of how microbiogas systems could work here in Switzerland, what they can do or what they not can do, what's the limitation of those systems. And as we're in Switzerland, we have a lot of alpine regions as well. So there's a lot of questions. What about using those systems during summertime in some Alps for, these mountain inns for hikers or for those places where we produce this famous Swiss cheese? Is there a chance to do that? In general, the biogas sector in Switzerland is well developed. It started, I would say, in the 70s. It became very professional. Composting was always a big thing in Switzerland, so people were used to deal with biomass and residues of that and food waste going into composting, and AD has now overtaken the composting thing here in Switzerland. So we're doing more AD and a lot more post composting, as we call it, to provide energy, to provide fertilizer for gardeners and also for agriculture. And there's a lot of different types of biogas plants, but they are all the time, they're pretty big, they're not very small. And as we are a small country with small farm sizes, our aim is to look more into small scale AD systems in Switzerland for farms, for food waste, for tiny houses, whatever. And we hope to give some more insights. And this is what I was posting on the internet, and Alex found me. And I'm really glad to be here to spread the word, to give you the information. And Wolfgang is staff of ours, an old friend of mine also. We studied both at University of Hohenheim in southern Germany, a university very dedicated to biogas research. And now we're doing applied research together here in Switzerland. And that's more or less the microbiogas project is his baby. He's doing all the measurements. He's installing all the stuff. He's really into it. He's getting dirty, as I always like to say. And I'm just responsible for promotion. So he will give you the presentation now of what we do there. And apart from being lecturer and being a researcher in Switzerland, I'm a member of Task 37 from the International Energy Agency. The task is called Energy from Biogas. So I'm Swiss national representative. So we spread the word of biogas all around the world. The United States is not a member, but Canada is a member. So there are a lot of countries joining together, spreading the word about different biogas systems. And I'm a member there. And for the next triennium, which just started, we have this small scale biogas theme as a for a report now I'm responsible for. So we will look into microbiogas systems all around the world, because we know from our visits all over the world that there are many biogas plants, alone 40 million in China, and we know that 95% of all of those systems, they're not running at all. So what's the reason for that? We want to look into it, and I just post you later on in the chat the website of Task 37. You can also oh, someone did it already. Thank you, Alex. So there's a lot of information. There's also a LinkedIn site where we post regular our information. So I spoke a lot now, but I wanted to introduce ourselves a little bit. We're really happy to share information with you. And yeah, I wonder now who you are, and probably hand over to Wolfgang to introduce himself. Thank you very much for having us.
Yeah, thank you, Hajo, and also for the introduction already of me. So I'm researcher at the Zurich University of Applied Science. So I'm here since 5 years. So I did my PhD on topic of high pressure fermentation. And now I'm focusing more in project, for example, for power to gas, how we can use hydrogen and making methane out of it to inject into grid. That's one big part of our group, what I'm doing, so power to gas systems, but only the biological way and not the catalytic way. So how we can store energy when we have a surplus of energy, because let's say a big thing about increasing renewable energies is the lack of storage capacities. Let's say in summer you have a lot of sun, you have a lot of wind, and in winter times you need a lot of heat. So the question is how you can get, let's say, energy from summer to winter, and that's why we're thinking why we couldn't use the distribution network of the natural gas, which we have a big one in Europe, where you can store up to 3 months of natural gas for whole Europe. So big storage is there. So why we can't use this with other kind of systems when we have a surplus of renewable energy, and then we're going from electrical energy to gas and store the gas, and then later on when we need it for heating, we just burn it, let's say, with units. That's the main focus. I'm normally focusing on project, but I'm also have the applied projects, for example, like this, where you want to deal and see how is such a plant built, how we have to adapt such a kind of plant for, let's say, this weather conditions here in Western Europe or Central Europe. And yeah, what's about the balance? So how much energy I have to put in, how much energy I get out. So that's the focus of the project, but that's enough from me now for the introduction. Then I would hand over to the other colleagues that they introduce themselves.
So yes, just have a quick go around. I would say I'm just going to call on people. Margaret, then Piper. Just introduce yourselves.
Sure, I'm Margaret McCauley. I'm with the United States Environmental Protection Agency, and I'm based in the Pacific Northwest of the United States. So I'm sitting in Seattle, but my office covers Alaska, Oregon, Washington, and Idaho. And in Alaska, we have a bunch of issues around sanitation that were written up in our original Clean Water Act, and yet still persist. And so trying to connect to all the different researchers around the world who might have some help that we can go farther together, as it were. So that's me. Piper?
Good morning, I'm Piper Peterson, and I'm in the Seattle, Washington office as well. I mostly clean up Superfund hazardous waste sites for my day job, but have been pulled in for the last couple of years to help facilitate this project, and handing it over to capable brain trust, including Alex, as I look forward to retire later on this year. So, but fascinating work, and really pretty shocking that some of our waste management, especially in tribal villages, is in the state that it's in 2025. So it's been a fascinating journey, learning lots of things that you guys all work on, and who knows, maybe I'll come and work for free for a few months in Switzerland and help you all out. I can dig in the mud with you.
This is being recorded.
Well, I'm only after I'm retired. This isn't part of my
Gotcha.
day job. You're not a consultant that I'm paying.
It's on the record, just so we know.
It is on the record.
Embray, then Robin, then Nate.
Can you guys hear me? Awesome. I'm Embry Bronstead. I'm a wastewater engineer by training, but these days I mostly just cat herd, project manage projects for an environmental consulting firm. But I have been very passionate and evangelical about waste to resource projects, RNG, all of the other cool things that you can get out of a digester. So this is great. And I also will say, if you guys don't mind, my husband is actually going to be on sabbatical at AOVAG the later part of this year. So I might just drop by and check out your research plant, if that's okay.
Yes, please. Robin, and then Nate, and then Simona.
Okay, hi everybody. Depending on whether it's morning or afternoon for you, it's afternoon here in the west of Scotland, which is where I'm based. My general background is, as was mentioned by our Swiss folks today, mostly in large-scale waste management AD. And in fact, I started my AD journey with a big company very close to them called Biogas, based in Zurich. So I know exactly where those guys are located and projects around them. So I look forward to hearing from them. Most of my work is very big scale, dirty, nasty business, mostly waste, very rarely poop related and sewage related, as much of the discussion in the group is here. But a big diversion for me over the last year has been related to this group, and I want to see this group succeed at the complete opposite end of it, because I think big business and increasingly things like the energy businesses that we increasingly get involved in at the very big end of things, the big petrochemical companies still need to keep their feet on the ground in terms of social impact. So these small projects are really important, not just to the individuals that get impacted, but to the big businesses that often look over and above them, but they actually need to do that. And that's what I'm trying to, in the future, sort out from my side. So west of Scotland based, right on the edge of what you'd call the cold climate, but often isolated climates in our islands in the west of Scotland, and also a lot of my work has been in Scandinavia, so often isolated, even if not cold communities. So what you do in this group is 100% related to all of that. Okay, so I look forward to the next steps, as they say, and the next person. Thank you.
All right. So my name is Nate Janiga. I'm in Seattle, Washington. I work for Corollo Engineers as a consulting engineer. Previous to that, I worked for 6 years building MBR wastewater treatment. So anyway, I am a wastewater nerd and enthusiast, but like Embry, I've always been into anaerobic digestion. I was before I even did wastewater engineering. I thought it was so cool. I got pulled into this group because I was working, and I'm still a member of the Mount Everest Biogas project. So again, looking at a really cold, remote area, that project is seeking to treat all of the climbers' waste from Mount Everest in one of the highest villages up in Nepal. It's a very lofty goal. We have not raised like $300,000 to build that as a pilot. So looking at these kind of micro AD things, and the pilot project that we're working on in Alaska to kind of have a proof of concept for the Mount Everest biogas project would be a great stepping stone to move forward, instead of just trying to go drop a treatment plant up at the top of the world. And I'm very interested to hear what you have to say today. Thanks for presenting.
Thanks. And I think I'm next. I'm Simone Saballo. I'm the Deputy Director at Zender Environmental Health and Research Group. We're a nonprofit out of Anchorage, Alaska. I have background in environmental engineering, and I'm a waste and honey bucket nerd, I guess. My master's was testing prefab compost toilets as an alternative to honey buckets in Western Alaska communities. We work with rural communities in like all across Alaska on a very regular basis, you know, daily, weekly, monthly. And our primary focus is solid waste, but the, you know, honey bucket waste just always crosses over, whether it's honey buckets being dumped at the landfills or just communities calling us wanting help with their honey bucket situation. So there's a definite crossover there. And yeah, so yeah, love this group, and I fortunately cannot stay on that long today because I've got a conflict with another meeting. But I'll pop in anyways. Thanks.
Ariana, and then Anne, if you can.
Yeah.
There you are.
Hi, there I am. Thanks, Alex. Hi, my name is Ariana Monroy. I am also with the U.S. Environmental Protection Agency based in Seattle, Washington. I review a wide variety of projects in Washington, Oregon, Idaho, and also Alaska that have federal nexus. And so when I review these projects, I consider a variety of environmental impacts to different media such as air, water under the Clean Water Act, land, etc. And so I'm here to learn about new technologies that could help treat waste and keep up to date with these projects that could be happening in Alaska and other cold regions. Thank you.
And I am Annie Corrigan. I am at the National Renewable Energy Lab, which is based in Colorado, but I'm specifically at NREL's Fairbanks campus. So I'm up in Fairbanks, Alaska. And my background is more in energy. Most of my job is in technical assistance, doing energy planning for often communities in Alaska, as well as other programs nationwide. But I am involved here because I was handed actually a project when I started at NREL about a year and a half ago now, that was this EPA pilot study on anaerobic digestion. So this was kind of the first big project that I took on at the lab here. So it is of EPA's, the Environmental Protection Agency, their design based off of some prior research they had done. And NREL, with a campus in Fairbanks, Alaska, was able to do this cold climate or seasonal anaerobic digestion pilot experiment, which I'll be talking about later. So I am not with a technical background in AD, but I have been learning since starting on this project with, you know, I've had my own personal interest in waste and circular economies. So it was pretty interesting to me, but I certainly come with a lot of questions. And this group has been like instrumental to understanding and helping getting this pilot set up for success, hopefully this season. So we can talk about more later, but thank you all. Oh, I'll also note, Alex, I have 1 hour from now before our next NREL team meeting. So I know I'm supposed to talk, just wanted to flag that for time. And Margaret also has the slides and we'll take notes on any continuing discussion because I have some questions at the end for our own side of things. Thanks.
So I think I'm trying to remember timing here. We gave the Swiss project 40 minutes, I think. Is that right? I don't remember now. 45 minutes, something like that. So it sounds like, Anne, you might, by the way, you're Annie and Anne E. So I can say Annie, I think. We can, I think, have your project before you leave, maybe. We'll see. And if not, then Margaret, is that what you're saying?
Yeah, I just wanted to flag that in case.
Yeah.
I think the conversation about the Swiss project will also be really interesting. So I just wanted to flag my time constraints up front. I think we're planned to have it all wrap up within the time that I'll be present, though.
It is possible to switch the order potentially. I don't know if that's a good idea, but could talk about it.
I don't want to keep the Swiss up past their bedtime.
Fair enough.
Thanks a lot. Okay, then should I just start that we're not getting too much another schedule? Okay, then today I'm going to present you something about the insights, let's say, from the project we have, which is called Biogas. And let's say also about all the challenges for sure, which we have when you're dealing with this kind of systems. But let's say I would begin with some slides about introduction, or let's say the background, why we're dealing with this kind of systems. So we noticed this small or micro biogas plants, they exist in a lot of different types. They are simple, they are normally robust systems, and they already used in numerous warm climate regions for sure. So normally they are easy built, so they're just a bag, let's say, which is the digester. You have another bag as a gas bag, and then normally using for heating up stuff or cooking some stuff. So that's normally a simple type of system. But for sure, also we are dealing here in all over the world with current energy challenges, let's say. So we are going more from fossil fuels to, let's say, renewable energies. And so this means also that the energy prices for sure are rising because they're more expensive when the fossil prices are still low, let's say, in comparison to that. And what we're also talking more about is about energy shortages sometimes. Probably in winter, let's say, when you don't have wind, you don't have much of photovoltaics, let's say. When you have just renewables, wind and photovoltaics, then probably in wintertime you have some challenges that you can have enough electricity or energy for heating. And for sure, like you all do, we want to reduce the greenhouse gas emissions, and we want to have a sustainable energy supply. And we're also talking about autonomous energy resources. Let's say that you don't have a big grid, or some, let's say, plants or let's say houses are far away from grid, but they're still having to deal with, or to get some energy. They need something for, let's say, heating, for light. And they normally also have wastes, organic waste, which they're generating because people living there, they're eating food. For sure, there will be some organic wastes. So why we can't use them also? This also deals then with the waste management. And for sure, when we're talking about, for us, it's not waste normally. Normally it's like nutrients. All people always saying that's a waste, but let's say organics is not a waste at the end. There are nutrients inside, so they have normally, let's say, still things inside which you could use. It's not just to just burn it and that's it. So we also have to think about closing cycles. And let's say different probably to US is that we don't do any landfill since longer time. So we have to close more the cycles. This means, we are dealing. So we have to deal somehow with the things. So we can't just building big hills or mountains and let's say later on we can deal with this. The only thing where we now building hills, when we're thinking, for example, about phosphorus recovery, I don't know, it's a big challenge, let's say, for us, or there are laws that, for example, we have to get more than 50% back from the phosphorus from the sewage sludge. And let's say that's a big thing to deal with this because you're not allowed to put any kind of sludge on fields. So normally we burn this. So now the company is thinking about to have, let's say, one central station where they have the mono incineration to burning all the sewage sludge, and then they're building the big mountains of the ash. At some point, at some day, they will have a leaching process to get the phosphorus out of these mountains. But let's say the incineration plants they have, but the leaching process is not done yet. So that's also kind of not really landfill, but at least just also building hills, and let's see, dealing with this later. And let's say the motivation for us was that this kind of plants, which are already used in, let's say, a lot of different warm countries, if it's in China or in Africa. So, but we don't know if we could use this kind of systems in colder regions, let's say for Central Europe. Probably we have to adjust this kind of systems. And what we also don't have, we have a lack of data, let's say. There are millions of these plants, but nobody is measuring anything. So they see if the burner is working or not. That's, let's say, the only measurement equipment they have to see if it's burning or not. So they know the gas quality then, it's enough methane inside. But normally they're not measuring, and that's why we also deal with this, that we say, okay, we want to have some scientific study to really like measuring different kind of temperatures, pH, redox, gas amounts, gas quality, and all this stuff to do also a balance, let's say, later on for the energy. And for the economic feasibility studies, you also don't find a lot of information about that. And especially, let's say, in Central Europe, there are none of these businesses. And big thing is technical, everything is possible, but for sure, the authorization practice is always lagging behind, because when you don't have this kind of system yet, so there's no law or regulation. So there's always like this. First, you have something new, and then the regulation comes later, because before they never had to deal with this kind of things. So this was the motivation, and let's say what we want to do in this kind of project, which is dealing for 2 years, is to analyze the performance once, so that we operate in these kind of plants. Then also that we, what do we have it here? That we have the economic viability to measure this, and how it's about the permission. What do I have to do to get this thing run, and also what kind of let's say offices I have to call, and who is deciding if I'm allowed to do this or not. And for sure also have a look on, we do some 2 meta studies where we want to have a look how we can use this kind of systems also for, let's say, regions which are really like far away from grid. So let's say, for example, the Alpine region, and see what kind of, probably there is a possibility to use this kind of systems. So these are, let's say, plus minus the working packages we are dealing with. So the first thing was first to construct and plan such a thing. Then for sure the operation, which we're doing now for 200 days already. And for sure, when we did the construction, to adapt the normal system you can buy, let's say, on the market to these conditions we have here. And for sure, putting a lot of different measurement equipment inside to do the scientific research, and get also some practical experiences, let's say. Because let's say when we are saying, yeah, so when we're doing scientifically, you would say, okay, you, for example, feeding like three times a week. But for sure, later on, it's not the reality, because we are thinking about this kind of small plants which you're building. Let's say households have one of this plant, so they will not do it every second day. They will do it probably sometimes more, sometimes less. So that's the reality later on. So that's what we also want to focus more. Let's say at the beginning we did it like 3 times a week, but now the people which are living there, they have to operate, and now sometimes they're not feeding for 1 week, but that's, let's say, the reality how it works. Good. Yeah, and then we want to collect, let's say, 12 months of measurements, and for quantify the performance, the energy, and also the economic efficiency. And then for sure, let's say the 2 meta studies to the legal authorization and the potential for small houses and Alpine hospitality businesses. And let's say the project started in December 2033, and we have different partners. So we are from, let's say, the Zurich University of Applied Science, and we are from the Institute of Chemistry and Biotechnology. But we also have colleagues which are helping us, which are from another institute, the Natural Resource Sciences. And then we have this company which is selling this kind of biogas digesters already in Africa, for example, BioEnergy. And then we have the Synergy Village, that's where we installed the plant. That's, let's say, a community, or let's say, yeah, community where people living, also volunteers, where you have a lot of people there which probably can deal with this kind of biogas plant. That's why we placed there the biogas plant. And the whole system is funded, or the project, from the Swiss Federal Office of Energy. So to get an idea what we installed, here's a easy scheme, what we did or how it looks like. So this means first we want to characterize the substrate which we are feeding. Normally it's, let's say, kitchen waste which they're dealing with. So we're not working with sewage sludge or poo or anything like this. We're just using, let's say, kitchen waste. So there we want, for the mass balances, they have to weigh the substrate which they put inside. We're doing, I think every month we're doing organic trimatter content, and for sure we're doing the same with the digestate which is coming out, to see how much digestate is coming out, what's about the quality when we think about the fertilizing later on. And what we're also doing is the residual methane potential test. This means normally there shouldn't come any gas, because how we operate now, the retention time in such a biogas plant for us, it's around 100 days. So it's easy that everything is degraded. Let's say normally you have biogas plants which having probably 30 to 40 days retention time. We have much longer retention time, so we're not expecting any residual methane potential with the substrate. And then because we want to be scientific, for sure we have to measure also things like online. This means we measuring, for example, temperature in different places. So we're measuring the soil temperature, we're measuring the temperature in the input and in the output. So we have there a combi electrode with measuring pH, redox, and temperature. So in two places. Then we're measuring the, let's say, temperature in the gas phase, but we also have another temperature measurement, let's say, between the heating system and the bag. Then we measuring also the gas quantity with a Ritter gas counter. And then we have also sensors for methane and CO2. They're working, yeah, let's say, sometimes good, sometimes not. They are not normally used in this kind of, let's say, for outside and let's say temperatures below 15 degrees. So there we have some challenges with this measurement, but we also doing frequently measurement with a mobile measurement unit from a company Träger, where we also measuring the methane, CO2, hydrogen, and H2S also. And what we're also doing, which is not mentioned here, we didn't have the budget to buy, let's say, a solar panel to produce the electrical energy, or let's say the solar voltaic or solar thermical energy, which we couldn't do this. That's why we just using the energy which we get from grid, but we have counters for measuring, let's say, different equipment. So one measurement is just for all the equipment, the measurement equipment which we needed, because normally you don't need all the stuff when you're operating this biogas plant. It's just for scientific. So how much is just for the measurements, how much energy we need for this. Then we have the big one for the heating. So how much is the energy we need for the heating. And then we have two other measurement units where we can measure the, just in case if we want to do a pre-treatment of the substrates which we put inside, for example, like mixing, that we cut them, or that we have to hygienize them when, for example, you're using not just the kitchen waste, but other stuff. So that's there we also have measurements which you could do. That's just the easy scheme for this. And let's say the biogas plant which we're using, we got from our project partner, B Energy. So that's a former colleague of Hajo and me. So she was doing her master's at the university, and she invented this called biogas backpack. So not the biogas plant itself, but the biogas backpack. Let's say because she always thought, let's say in Africa, a lot of women have to just get, let's say, things for cooking, let's say fuels, normally like woods or something like this. So they spend a lot of time just getting some wood to cook later on. And she invented this biogas bag where she said, okay, why they can't use the biogas plants, let's say in a community, and then they have the gas bag, fill the gas bag, and then 1 cubic meter of gas you can cook probably 2 to 3 hours, and it's just not heavy, because let's say 1 cubic meter is 1 kilogram, so easy to carry for even like children. So that's what she invented. But when you see this kind of biogas plants, you see normally they are don't have any heating system because they don't have heating issues. So normally it's just, let's say, a digester bag. And so we had to optimize it with reliable measurement, and for sure, because we are here in colder region, heating and insulation systems. And where we are, so probably some of you went already to Switzerland. Let's say we are located near Zurich. So our campus, the big campus is in Winterthur. So that's the headquarter campus, but we have one other campus here in Wädenswil, where we are located, let's say, on the Zurich Lake. And on the other side of the lake is the Synergy Village, where we also install the biogas plant. This means when I want to go to biogas plant, I have to use a ship going to the other side of the lake, and then you can go there by train, or you can go there by bike. So it's a nice, let's say, way to go to work. Let's say when there's something not working on the biogas plant, it's not a big deal. So you're just taking the nice ship, have mountains, let's say, in the background, so it's not the worst way to go to work. So this Synergy Village is, let's say, a non-profit organization. and they are dealing with different kind of things there. So they have a look on environmental impacts, and they have a lot of volunteers which are working for them. And what they also have is, I think they built it five to 6 years ago. They built they got a project and built their tiny house, let's say in near to their older farm. So they installed a tiny house where they measuring, or so producing energy. They measuring the energy. They producing, or they measuring all the energy they're using. Also the gray water gets treated. They have they have a toilet where they separate solids and liquids. And they also taking the gray water later on to grow some crops, let's say, on top of the building. So that's why we said it's probably the perfect place to install a biogas plant next to it, because they're already dealing with this kind of sustainable things. And in the project, just for introduction, we also want to deal with, let's say, later on with the small apartments. So they normally far away from sanitary facilities. So that's why probably they have to deal also somehow with this. Where probably you could use this later on is probably winter gardens and natural building materials. They normally use in recycled materials and nutrient recovery. They also have to do normally in these houses. So they have organic waste. They have to deal with this. And normally they also need some kind of electricity, also heat. So the question is probably this kind of small or micro biogas plants probably can give them some heat or electrical energy, or at least energy for at least cooking. That's normally the simplest way. Just burn it, let's say, with a cooker, and then you just produce your food. And the other thing is where you have a look on is this alpine pines inns, where you're saying it's far away from grids. They are normally, let's say, in winter it's cold there, in summer it's warm, let's say. And what we also have to deal with this kind of inns is normally sometimes some of them are just operating in summer, so they are not used in winter times. So the question is, when you have this kind of biogas digester, what you're dealing when you're just operating for half a year, and what you're doing the other half year, and how you start then with the in summer again with this biogas plant. So that's a big task for us. And there we see normally they are far away from grid, and they need energy somehow there, at least for cooking, because they are living there, so they want to cook. So why probably these are good parts where you could use this micro biogas plants. And at the beginning we planned first, so we had a look, so what kind of equipment we need. So we have different streams, let's say. We have water, we have here it's waste or green waste, for example, from gardening. In summer more, in winter you don't have. Then you have kitchen waste. And here you see that's, let's say, a pre-treatment method, which you could use for just cutting or for hygienization. And then you have a fermenter, and the fermenter is producing the gas, which you're measuring and which you can store. And for sure, they're also producing a digestate, which you normally can use as a fertilizer on field. And we need to have a look, so where we install it. So let's say that's the part from the farm, let's say. And here is this tiny house, and we built it, let's say, next to the tiny house, because we were thinking probably you could use also this kind of gas for heating up, let's say, their greenhouse, which you have on the roof, because they're not heating the roof. And she had, I think, orchids, and she said that probably would be nice to keep them alive, and said, yeah, I don't think that in wintertime we produce a lot of energy which you could use. Normally we have shortage also for sure in winter times. And let's say that's the layout, what you normally get when you buy this kind of biogas plants. So normally what they're giving you is, let's say, a digester bag. There are different sizes, so from 2 to 5 cubic meters she has. And normally, let's say, all the piping she is normally not selling, because they're saying you can buy it, let's say, on even in shops next to you. So why should I just transport it to you? So that's also what they're doing in Africa. So she normally just giving or sending the biogas digester and all the piping they can do there on their own, just to reduce the amount of things you need to transport. And for sure, what we had to do, this we'll talk later on, we had to adjust it somehow, because normally this biogas plant is not in a greenhouse, and normally you also don't need a wooden hut. It's just for the wooden hut was for us to put all the controllers which we need, that they are not getting wet, and to store things. And for sure the greenhouse, that we can also work there at least when there's winter time or when it's raining, and we still, let's say, can work inside without getting wet. So what we're using, because sometimes it's interesting, we thought about how we do the automation. So we use the really cheap, let's say, automation possibility. So probably you're familiar with Raspberry Pi controllers, and there's a company where you can buy this Raspberry Pi, which are more industrial, let's say. So you can put just into a control cabinet, and then you can put just different kind of modules on it. So if you need, let's say, analog signals, digital signals, or you have to, for example, to deal with heating systems, to control heating systems. So, and we use the software Node-RED. Probably some of you know this. So that it's just a software which is installed on Raspberry Pi, and you can just, let's say, easy just generate and do the automation. So it's just, you don't have to do hard coding. It's just modules which you just have to combine, and that's it. That's easy. And then we're using also Influx database, because they already had this Influx database for the tiny house, and we just put also our data which is stored there. And later on, just in case if we have time left, I can just show you the link where we have all the data. They see just real time all the data which you want. So how we started, let's say, so we did the plannings, then we got all the things, and that's how it started, let's say. We did a workshop with her. So that's Katrin Pütz, so the founder of this bioenergy company. Also, we did a workshop. So I think we were in total 7 to 8 people which were just interested. So how we can build just kind of biogas plant up, and then we did this. So we digged a small hole, put the biogas back there, the digester back, and then we had the roof just in case if rain is coming. And let's say at the end it looked like this after the workshop, and it lasts, let's say, for 2 weeks, and then okay, we were sure before that we have to adjust it somehow, but we had to do the workshop. But for sure, for the weather conditions we have here, it's not feasible for us. So that's normally when you just buy it, it looks like this, let's say. So we did a lot of adjustments, let's say. First, we did the surrounding area. We cut back some trees that we have more place. Then we digged a bigger hole, installed, let's say, the heating cable below. Then we did the insulation also there. Then we had this wooden hut where we put all the electrical stuff inside on controlling units. And then on top of it, we're building this greenhouse. So this looks when it's, I think, in the autumn. That's how it looks in the winter times. And then for sure, these greenhouses are also not made for Swiss conditions when you buy it. That's why we had to make it more stronger, especially the roof, because normally it's just plexiglass, and plexiglass really thin. I think it's, I don't know, 3 to 4 millimeters. So it's not made that snow is, and so it's okay when the snow, when you don't have this wet snow, when it's just a dry snow, when it's just going down. But when I have the wet snow just sticking there, I went there once, and then the roof was, let's say, half. Some of the things just put inside. That's why I say, okay, that's not, I will not manage with this anymore. So that's why we had to put there also some wood to get the roof stronger. And here you see, which we also bought, which we sometimes use and sometimes not. It's just, let's say, a mixer, which you can buy, let's say, for kitchens. So it's, I think, for 7 liters, just in case if you want to cut some things. And then when we dealt with this kind of heating system, which we got from this company, we said, okay, this is not gonna work. Let's say one is the power of this heating system, and the heating system is laying below this bag. This means the connection, let's say, to the liquid inside the reactor is really low. This means it's not efficient. So what we did, or what we had to do, is to install another heating system. The problem was the biogas plant was already operating. The gas was the bag was full of liquid or manure, let's say. So, and I said, okay, 2 cubic meters of manure. I don't want to get rid of this. And then to put something inside. And then we said, okay, what we can do now. So there are not much options how we can improve it. And what we did, or what we found, is also another kind of heating cable, which they're normally using in ponds. So just that the pond is, when you have fishes in your pond, in winter times, you can heat up a little bit your pond to some degree. And let's say what we put inside from the output, we put there 40 meters cable, heating cable, and put it, let's say, later on in this bag. So we have 40 meters of this cable inside. I don't know how the distribution is in the bag, because you just put it in. We're lucky that it worked. So you see also that, let's say, in the front of the biogas digester, the heating is not so efficient than in the back. This is probably because, you just put it, let's say, later on. For sure, when we would do this from scratch, new, I would first install all the things, then I would fill this biogas digest. But that's the lesson learned from us. Yeah, and then just some results. So we are not finished yet. So just to give you an overview what we're doing and what we're measuring. So these are, for example, the measurement of the pH. Let's say the front is, let's say, on the input, and the rear is, let's say, the output. These two pH probes we have. And you see, let's say, at the beginning, we had a pH of 8. Let's say when we started, well, first we did the testing with just water inside to see everything is gas tight, everything is tight. And then we just took or got liquid digestate from a biogas plant. It's also compo gas biogas plant. And we just inoculated with 1 cubic meter of this. Then you saw at the beginning, the pH was high, but because there was still a lot of water inside, pH decreased. And for sure, you start with the feeding. And then later on, I think around here, we inoculated one more time with just 2 cubic meters of manure, because manure has a lot of, let's say, a big buffer capacity. So then you don't have these problems when they're producing, or when the acids are generated. What we're also measuring is the redox, because it's a combi electrode. So redox, you all may know that, let's say, when there's oxygen, normally the redox is positive. Let's say that's why at the beginning we measured, let's say, positive millivolts. And then when you see that's getting more and more anaerobically, you see that you plus minus at minus 300 millivolts at the end, what you're reaching. And temperature, there you see, let's say, all the temperature sensors we have. So we're measuring ambient temperature then in the control cabinet, in the digester, then also in the front and rear of the digester. Then also for the gas counter in the greenhouse, below or above the heating system, and also, let's say, in the gas counters, because the gas counter, for example, works like this. There's water in the gas counter and it's turning, and for sure we had to make sure that it's not freezing in winter time, but otherwise the gas measurement is not working. So that's why we have a special heating system surrounded on, or put around this gas counter to make sure that at least has 6 degrees centigrade. And what you see, that we're reaching temperatures inside or in the soil, let's say, plus minus up to -4. But you also see, let's say, here the heating system worked at the beginning well, and then sometimes you have these interruptions. Let's say that's sometimes when the controlling unit had some failure or errors and nobody's taking care. Then sometimes take longer. So this like having a child. So it's even in it's fully automated. Sometimes you have to, or you always have to take care of this. It's not fully automated always. Just always have a look. Not, let's say, every week, just because then it's not working. But you see, we're reaching with this heating system, because the heating system has a max of 40 degrees. Let's say the cable has a, how it's called, it's measuring the resistance on its own. This means when the outside around the cable gets too hot, or because you're heating it up, then it's reducing the electrical power which they have. So the maximum which they have is, I think, 1,500 watts, which they have a maximum, but normally it's just reducing really fast to keep just the temperature. Then it's going down to 700 watts, for example, just half or less, to keep this 40 degrees centigrade. And what we're also measuring is the gas production with these gas counters. Let's say that's what we did up to now in this 200 days. So you see at the beginning, was not that we didn't produce any gas. It was just there was no gas measurement unit installed. That's why it's 0. But you see it's not always stable. So sometimes, or you see always on the gas production, if somebody feeds the reactor or is not feeding. So you see sometimes here, for example, probably there were some vacations and then just nobody went there to feed up. So then you just have no gas production. But in total up to now we produced around about 14 cubic meters of biogas. That's from the results, which I can present you now. And let's say conclusion, let's say the plant is now operating. Now let's say 3 weeks ago, we handed over to the Synergy Village people. So now they are responsible to feeding this, to have a real feeding, let's say. And you saw at the beginning, they were not so strict in feeding. So this means nobody was responsible. And when nobody's responsible, the biogas plants gets no food. And so it gets, for example, last, I think 2 to 3 weeks, I think they only fed it for 2 or 3 times. So really, that much less than we did before. So that's a lot of things which you have to do, which is no technical challenge, but it's a social challenge which you have to deal with. What you also still have to do is the laboratory analysis, let's say the organic dry matter and the dry matter. And we also have now a bachelor thesis, which are dealing with the methane potential test and the residual methane potential tests, where we want to just take samples from there. The question is just always for sure the kitchen wastes are not, let's say, homogeneous, because let's say probably in January they cooking some other food than in summertime or in wintertime. So this means what is a representative sample. So for sure you can take now a sample, but probably in 2 more months it's something in another food. That's why we're taking different kind of samples. And what we also still have to do is the meta studies on this alpine inns. Good. And I don't know if Hajo is still there or not. I don't think so.
He stepped out. Yep.
He stepped out. Yeah. Then what he normally shows is this Swiss Army knife, what biogas is for us. Let's say it's just handy like a Swiss Army knife, and you can do a lot of things. And that's what we normally promising, let's say, and every child would understand. So Swiss Army knife, everybody knows, and it's a tool for do different things. And that's what we also think about biogas. So it has the potential to, let's say, treat different kind of organic wastes. We can produce fertilizers. We could produce also energy or also other products. This means biogas, let's say, it's in the center of the so-called bioeconomy, let's say, and it's there to treat different things. It's not always there to produce fancy new stuff. It's just to get rid of stuff which other produced. So that's the task what we have to do with this biogas. That's why it's in the center of bioeconomy to deal with all the side streams which the other processes have. Yeah, and with this, I'm coming to the end of my presentations. So that's our team we have. And let's say on the right-hand side, you see how we actually just using now the biogas, let's say. So we have a cooker. At least when you're there, the problem is that nobody's using this biogas there in the Synergy Village. So this means when I'm there, I'm always drinking a lot of tea at least and burning it, that not methane is emitted, but at least that we get burn off this biogas plants. But we're thinking, or we have other cookers now where we're thinking about how we could use this kind of systems also with this biogas backpack to, for example, have a barbecue somewhere else. Because when it would be a barbecue, probably they use it more often, because just doing a tea probably is not fancy enough to deal with this. Yeah, and with this I would end, and thank you for your attention, and I'm happy to answer your questions, just in case if there are questions.
Thank you. So that was pretty much on time. Anne E, are you? Yeah, thanks. And I think, so Anne, I think this will be time for you. Let's aim for like 5 minutes of questions, and how about we raise hands on our little doohickey here, and you can close the presentation, and we can see whose hand is raised. and go back to slides if we need to. So
Yeah.
go ahead. And if somebody's not able to use hands, just shout out. I'll demonstrate. Ambre, go ahead. I was going to ask something, but you go first and then I'll go.
So I was just curious. First of all, this is awesome. I think everybody on this call is geeking out. I did have a question about the kitchen waste and whether or not you allowed like proteins, fats, or if you try to keep the feed to like just the fruit and vegetable kind of waste, or if you take everything.
Let's say up to now we're using all they have. Let's say normally, let's say by law or regulation, let's say when these kitchen wastes are, for example, like from a restaurant, let's say it's commercial, it's not on your household, then normally you're not allowed to do this. So you have to do the hygienization, and then you allowed to use this kind of things just for things because they're pathogens and they were already like in touch from us. So that's why you can't use them. But let's say when you're doing this on your households, you could use whatever you want. And normally some of us also have this compost, let's say in their garden. So you can just put all the stuff you have, which have as a waste, you put there on your compost. And the same we are doing also with what we normally do. We have this collection of the organic waste. So you have, let's say, where we have just the organics, and then take it and they doing biogas out of it with a big one. So, but for sure, let's say later on, we have to think about, for sure, for this biogas plants, when you just have, let's say, citrus fruits, let's say, for example, or just oranges or just lemons, then probably you would have a problem. But it's the same for us. Let's say when you're just eating lemons or just oranges, you don't have all the nutrients you need. This is the same for a biogas plant. The better distribution of everything, the better the biogas plant works, for sure.
All right, I'll jump in with a quick question. Does that get it, Ambre? Does that do it, or did you have some?
Thousands, but I'm not gonna monopolize. Go, Alex.
You'll visit. You'll be there.
I'll visit.
Yeah.
I'll visit.
Okay. I had a quick question, and then Margaret. That's the other hand I'm seeing. So, what I've heard about these long term is, or seems to me to be an issue, would be what about solids? Like, does this thing just fill up because you got a bunch of solid waste going in there? Like, do you have to add liquid to it, or do you recirculate liquid? I'm really concerned about the longevity of this device as being filled up with solids.
I think it depends what kind of substrate you're using. Let's say at the beginning, we did it for maintaining the pH. Let's say we normally did 50-50 of manure and the solids which you put in. But let's say the solids which you got from kitchen waste are really normally easy degradable. It's not like, for example, when you're using let's say green things from your garden. For example, when it's grass, it's a different story because they would never ever degrade like totally. You always will have some leftovers. But when you only have kitchen waste, when you don't put, let's say what we also had this avocado kernels, for sure you put it in and it comes the same out. So because the area is really like low, they can't attach and they can't degrade it, but you just get rid of this before. But I think with all the kitchen waste, you will not have any problems with the that's getting too solid, because normally they are degraded really fast and then it's easy. But for sure, what you could do is always, when it's, for example, the food which you want to put in, because you have this pipe that has some diameter, I think inner diameter of 100 millimeters. And for sure, when you have, let's say, solid stuff, it's really hard to get them inside. So you could also always use digestate from the output, let's say, and just using this. So you don't have to put new water. You can always recycle the things you have behind.
Margaret?
So I have to say that if a Swiss eco village is not motivated to keep using the technology, I feel like we're unlikely to get anyone else to keep it going. And so I guess if you have any thoughts on that social aspect that you identified, because it sounds like technically it's been smooth, but
let's say it was. But now let's say I went there I think last week, and then I had a talk to these guys which are there because also they are, let's say, in the project, and I said I also need data, and they have to take this responsibility to do this, and I say it's not so much of work for them, because normally the problem is when you have this keeping this kitchen waste too long, also let's say in your bin, just there for a week or so, then a lot of easy degradable stuff is just gone, so you just lost energy. So why you just have to clean it more often or to empty it more often, then it's easy. So the question is just because there are a lot of volunteers, the more people involved, the more difficult it is that somebody's taking care of it, for sure. When you have less people, it's easy because then you know this guy will do this and this and the other. When you have too much people, they always arguing the other one could do, or I thought you did it, and then nobody's doing it. That's why I talked to them last week, and now at least this week they fed 2 times already, so probably we have some changes. But it's the same with other projects we have. For example, we are also thinking about, especially we have this small scale biogas, small farm plants in Switzerland. So you have a lot of cattle, but not big ones, big farms. So the question is, it's not feasible for a biogas plant because biogas plant is not normally expensive and bigger scale. So the question is also we are dealing is how we can get, let's say, the nutrients or the manure, let's say, to a centralized biogas plant. Technically, it's easy. But it's always the problem with the farmers, because this one farmer who don't want to have digestate from these other farmers, which is his neighbor, because they have troubles since 100 years. So that's the biggest task you have to do. It's not the technical problem. It's always the biggest task to have the social challenges to deal with this and to solve them.
One more, and then let's go to Anne E. Corrigan. Who else? Anything else? All right, go ahead. I got one quick thing here, which is, I know you're doing NPK on the way out. It might be worth looking at NPK on the way in, both amount and form. I realize that you won't really lose any, so amount is almost not the issue, but form does change, and that might be pretty interesting for nutrient management. You're going to have different forms of nitrogen and phosphorus coming out than you had go again. So that might be worth a few tests.
Yeah, for you, especially for the phosphorus, what kind of phosphorus is there at the end? If this, let's say, plant available, or is just okay. At least we don't put any iron inside. It's not an iron phosphate where it's just there and you can't use it for any purposes anymore. But at least for sure it's changing. But let's say all the big biogas plants in Switzerland or also in Germany, which are dealing with kitchen waste or with waste from farmland, let's say, they always use it later on put it on the fields as a fertilizer. So they just have to calculate later on they have to do the balance with NPK if it's feasible. Let's say especially in this region where you have a lot of cattle, for example, north of Germany, or let's say from this region here in Switzerland, Luzern region, because they import all the food or feed for the cattle, but they don't have enough space, so they can't spread the manure later on the field. So they have to get rid somehow of the nutrients. So they have a big challenge how they get rid of them to put them or transport them really far. And that's for sure with the small biogas plants is not a big issue, but for sure later on when you think about when you have this on, let's say, alpine huts somewhere where there's not really like soil, where you probably have just rocks, then you also have to think what you're doing with the digestate, because on rocks you don't have to put the digestate, is for sure. So the question is also there's another issue which you have to deal with. Yeah.
I actually do have one question to make sure I got my notes right on this. At the startup, I think you said that it was 50-50 manure and feedstock at startup. Was that right?
Let's say when we did the inoculation at the really beginning, we just had water inside, 2 cubic meters of water to test everything. I don't want to have leakages and there's already manure inside because then it's a big mess. So the question is at the end, how we, or then we had, it was 100% filled with the water. And then the question was how we get rid of the water and put, let's say, the liquid digestate from biogas plants inside. And the problem was I couldn't empty it all because this armatures for the pH probes were like installed there. I couldn't just empty it full. That was just the purpose, because we did it with the measurement equipment, but normally you can just get the water out and then you just fill it with 100% of manure, for example. But because we couldn't like empty it fully, we had to put new stuff inside, and for sure it get diluted. And that's why we did first with liquid digestate, and later on we did this with this manure. Cattle manure is the best for this to do. We also have to have some structures. So we also use the not only the liquid but also the solids to have structure inside and big buffer capacity. And then when we start feeding with substrate, we did normally 50-50 with manure and kitchen waste to not get a big drop in pH too fast.
Okay, thanks. And what's the total volume of it, and how much did you usually volume of feed?
So let's say the total volume of this gas or this digester bag is 2 cubic meters, and depending on the retention time, how much you feed, it depends how much food waste you have. Let's say for us, this small biogas plant which he has is still too big for us. Let's say it's especially an issue when you have to heat up in wintertime all the stuff. Let's say for us, that's why we have this long retention type of 100 days plus minus. So this means plus minus maximum 20 kilograms or 20 liters per day coming inside. 2 cubic meters means at least 100 days retention time. Normally you should just use a smaller bag, which is probably just half a cubic meter, for example, would be the right size for us to have this 30 to 40 days of retention time. That's why it's important also when you're using this kind or other biogas plants that you really have a good looking on the potential you have, what kind of substrates you have, when do you have them, and what kind of amount in total, and then you have to do really the right calculations. Otherwise, you're wasting money for a lot of volume.
Awesome. Thank you.
You're on.
Welcome.
Okay.
Wolfgang.
Thank you. Honestly,
thanks a lot.
It's really great to see.
Yeah.
Thank you so much.
Also,
Then just in case, Alex, you just put the link there, just in case if you're still interested, or via LinkedIn, you can just connect to get some other insights from this project or other projects. So.
Great. Am I sharing my screen now?
Yes.
Sweet. Okay. My other takeaway with that was like, from that final commentary was just like, we're trying to do a lot of things in this little pilot. So I have some recap slides here because I wasn't sure how many new faces. This has been a while since we've talked about this pilot experiment. I know it seems like based off this crowd, we have a majority of folks who are pretty familiar with the experiment up in Fairbanks. But I'll give a quick recap just to remind everybody here, as I needed to remind myself. This is our design. So we have 4 different digesters. Each are 55-gallon drums. And the reason we have 4 is that there would be a different heating application for each of them. So gas capture systems are bell over water. They're outside of the sheds. The 4 different heating applications were, one is the control, it's outside. This is not walled structure. And we have one with this purple one is a heated blanket. So it's direct heat around the drum itself. Then we have this opportunistic resistive heater, essentially heating the space as possible within the shed. So this drum here is receiving some ambient space heating. Because of the way this is set up, we know that it's not exactly controlled because the unit with the heated blanket is also receiving that space heating. And then finally, we've got one drum in the greenhouse. All of this kind of heating system we described is powered from a solar array with a battery bank. So that's how this drum blanket and resistive heater are powered. This is just same thing, but from another angle to give you a sense of what is on site here. So last year we went through construction and we have all of this set up outside. But before I show you pictures of it on site, I wanted to take a closer look at the digester design itself. The drum on the right is what you're looking at, where our digester will be filled. You'll see here, synthetic feces is our planned feedstock. And we will be, I'll talk about this in a bit more detail, but that synthetic feces will be inoculated with samples from a lagoon in Alaska. So it will take, it's not exactly our local lagoon, but it is a lagoon in Alaska. So from their anaerobic cells at that plant will come, and that's how we will do what is planned to be a batch inoculation for startup of these drums. That is something I'll get to at the end for discussion, but this is kind of the overall view. So we've got a standpipe in the lid so that we can pump out digestate. And we have probes, and then we have a feed port also in the lid. So all the penetrations of the digester are entirely within the lid, and that was just due to leaking concerns. And then our monitoring is shown. We have 3 temperature probes within each drum. One is at the bottom, at the edge, and then at the core, kind of mounted on that standpipe. So that is to understand, how much mixing is going on. We do not plan to mix the drums except for at the initial inoculation. So this is maybe going to be pretty telling about how much movement there is without any manual agitation, if that temperature gradient is really extreme or not, and how that varies across the 4 different drums with different heating applications. So then the gas will be coming out of a pipe in the top, headed outside of the sheds and then into a gas capture system. So that's a well-over water gas capture system where we'll be able to vent or take gas samples out of the lid of the gas drum. I'm going to stop here just because that's a pretty quick overview most people are familiar with, but if anything I've missed identifying, is there any kind of questions here before I keep moving? And I know I'm just being sensitive to time here as well as I give a quick overview. But Wolfgang, yeah, if you'd like to ask clarifying questions, please.
Yeah, just a question, because when I see the feeding port, you're just feeding via the gas phase, or do you have a pipe that the substrate is going directly into the digestate or the liquid down?
So the feeding port is from the top, so it goes through the headspace and lands on the surface. And that was definitely something up for discussion in terms of where we could, if we wanted to penetrate the side of the drum. And for a number of reasons, that was because of that seal, the concern about the seal.
But this means from, let's say you're feeding it as a pipe, which is going till the liquid part, that it's not, you're not feeding via the gas phase.
You mean, is there a pipe from this feed port down into?
Yeah. Because this is what kind of reactor systems we normally use also in our former labs, to make sure that there are no losses of gases when you're just feeding, because you open and gas is coming out. So that's why normally you should have at least a bigger size pipe, which is going down till the liquid, that at least you're just losing this on the small surface gases, which are in the, let's say, pipe. And because with this, I don't know how much gas is just coming out when you just open it on top.
So I feel like I was hearing 2 things there. One would be, so there's a valve on this feed port where you would load, it would go in as fast as possible and you close it again when it comes to feeding. But the actual, there is no installed pipe here so that feed goes all the way down into the liquid at this time.
Okay.
It's technically potentially not too late because we haven't done our startup this spring yet.
Because I know from our small scale plants which we have in the lab, we did this with the pipe, because then you don't have to be 100% sure that's always tight, let's say, on the feeding, because it's just a really small surface where biogas can just go or just leave the reactor. Then probably you can think about if you're having just a pipe to make sure that you only have the surface where the liquid is and not the whole liquid surface where all the gas can, by mistake, can go out when just by mistakes of operation. Because for sure it's always about technical things, but at the end it's just how you train the people, and for sure you never can be sure if they're making the things right.
If there were I think part of the reasoning, at least, minimize gas losses, worth emphasizing. I think the reason that there isn't feed directly into this too is if that were to get clogged and not mixed, what issues would that present?
But you don't have the problem, even if it's clogging, let's say, because it's open on top, and you can just take a stick and just putting it down just in case it's clogging, because you open it and then you can just, when you're doing just a big diameter.
Yeah. We discussed the stick method, and our biosafety team didn't love the description of that, but
okay.
it's worth keeping track of things. Okay, so this is what it looked like during the construction phase. So we have our sheds built, and it was looking pretty good. This is the end of last summer, and we got the drums set up, and we have our solar set up with a planned power system. This is kind of while it was in construction. For those who have been following closely, I'll talk about the power system briefly. I actually probably won't spend too much time on this. Essentially, it's a PV array with that battery system I mentioned. This is for you folks who have some familiarity with the site. We had some surprise inspectors. I thought you'd be happy to see some of these updates while we were under construction. So the moose in the area have certified our operation. They've been all through the site. So this is something we actually did need to think about kind of critically, as we were wondering like if there would be disturbances to the system. And just keeping track of our instrumentation and our conduit and our pipes. So this is where we are now, and we've gone through the winter season. We haven't done anything except for this drum was filled with water for the season. So we were testing what the drum would do if it froze solid. It was filled up about 35 gallons of the 55, what we kind of tentatively had planned, and it froze solid. Nothing seems to have broken. The drum itself, expanded, but it was strong. And it is now just about finished thawing out all of the ice inside of that frozen solid drum. So we are talking about a spring launch at this time. And the snow has receded down off all of the panels and the roofs. So the next step is going to be May, June startup. Breakup is what we call when the ice all breaks up and flows out of the rivers. And the drum has also broken up, where we have now mostly liquid water again. We'll be able to dump that out in preparation for loading. And our plan is sometime in May or June. The lagoon is also experiencing breakup, and they expect operation to begin in late May. So we're kind of debating when exactly that's going to happen, both matching up when's it going to be the best opportunity for success with when are we logistically going to be prepared for our greatest chances of success on site. Alex?
So sounds like you had monitoring stuff in place, and you were monitoring like temperatures and stuff. So you have data from like the empty facility or whatever, which that's pretty interesting right there, and that will help, I think. So you have that already, right?
Yeah, so we didn't monitor throughout the winter. We monitored for about a month or two in August to September, which is when, that will be the anticipated, is the digester decline. When is that going to happen in the course of our year and our warm months? So we had at the end of last fall filled those 4 systems with water and made sure our monitoring equipment worked. So we have temperature data over that time, which could be informative for us estimating, anticipating, preparing for late season this coming year of monitoring.
Any other burning questions? You have to head out, right?
I do. I'm going to take another 2 minutes to get to my questions slide.
Oh, yeah. Sorry,
But
I thought that was it, but yes, please.
yeah, it is important. We only get together so often, but this is kind of a great touch base, and I hope we'll be able to talk again soon. So yeah, this is the current plan as we have structured. Now my head hasn't been quite as in this project lately because it was hibernation mode. And so we're kind of reevaluating, like, this is the plan we've sketched out. And before we move forward with it, are there changes we should make based off of what we've learned, based off what other have learned in the meantime? Because the biggest is kind of around the feeding and startup, because we really want to maximize our chances for success. This is overview of the data collection. We can talk more about that later, but the questions that are more burning right now are around like the ratio at startup. Originally, I think Max maybe had the first idea of just like one batch. Max is the other EPA colleague working on this project with Margaret and I. Essentially one batch, so fill it full and then inoculate it once, let it sit and develop residency before starting to feed. I think, Nate, when you visited Fairbanks, we also discussed maybe we should rethink that ratio, because at one point we were talking about 5 gallons of seed to 30 gallons of synthetic feces at startup. And that just might be overwhelming. Moving towards a 1-to-1 ratio might be a better plan of action, which means we have a far smaller volume in each of the drums to begin with. It's a whole bunch of headspace. And then based off of how that goes as the bacteria are establishing residency, then look at feeding. So it'll take much longer to get to what we anticipated to be full operating volume of the drums. I think that's kind of the biggest immediate question I want to stop on to get feedback from the group.
Nate? I mean, I think I'm the one. I think I was texting with Margaret, and I think she and I were honing in on the 50-50 to kind of get the microbial culture established, give them enough food, but also you also may want to be feeding a little bit at that time as well, because as your bacteria exhaust your substrate, you don't want them to go hungry, but you do need to give them a little bit of time to kind of get established. Nate, what were your thoughts? You came off mute.
Yeah, sorry, I was definitely waiting for you to go first. Yeah, I was having a little trouble hearing you, but can you give us that again a little louder, please?
I would advocate for a 50-50 split. Mix it up, give the bacteria a chance to establish themselves without any food limitations, and then start feeding.
Yeah, and basically that's the conversation I was having with Anne when I was up there the other month. So because yeah, before we were gonna have more substrate than inoculum, and I think it's 50-50, 1-to-1, whatever you want to call it. That's like gonna be just give you more chance for success. I know the previous lab studies that we did in University of Kathmandu for the Mount Everest Biogas project, they had a lot of issues initially with startup, and it was not until they went to basically a 50-50 inoculation or something like that. It was mostly cow waste, and then the cow waste, once they saw that established, then they started to use the climber's waste, which is a really gross substrate to use. And too much protein, and we were really worried about like antibiotic toxicity, all these things. So eventually we were able to show like, yeah, once you have a working digester, you can even feed it climber waste. but it was really about getting that established community and using, yeah, everybody loves the cow waste. That seems to have really good fermenters in it.
And it's alkaline.
I'd say two quick things. Oh, sorry. Let me just jump in. Gradual. That was the thing about Wolfgang's thing, whether he intended it or not, he couldn't empty all the water. So it started out really dilute. So it was inherently gradual. And it was a good question, like, how did he do it? But anyhow, then the other thing is, like, talk to Jaime. You know, he's probably going to have some opinions on these questions and couldn't make it today. But he can listen to the recording and might have some ideas. So yeah, gradual change in temperature, gradual change in whatever your feedstock is.
Yeah, probably a suggestion for the measurement. I don't know, let's say in Germany or in Switzerland, we're doing this so-called FOSS-TAG. So this means we're measuring the ratio as a titration, where we're measuring, let's say, all the organics, let's say, all the acids as a sum parameter, and then we compare it to the buffer capacity. So there's the FOSS-TAG. So it's normal titration. You're going from the pH you're starting till pH 5. And then you have all the buffer capacity is, let's say, all the sulfuric acid which you needed to get down to pH 5, the amount you can calculate in the buffer capacity, and then the rest from pH 5 to 4.4 is then the FOSS. So that's all the acids which are there as a sum. So that's what we are normally also dealing here with the biogas plants, because let's say pH is a really, let's say, challenge. It's easy to measure and online perfect, but it's, let's say, when you see something in changing the pH, then the buffer capacity is already gone. So it's really too late, let's say. That's why we're normally doing it, that we're taking the ratio between the organics to the buffer capacity, and it should be a normal biogas plant around 0.3 to 0.5 maximum. So that's what we're normally dealing with. So probably you can, I don't know if you have this kind of system to also probably measuring not only because you're also measuring the acids, probably you can do just the sum parameter of all the organic acids in comparison to buffer capacity, because then you see it much faster when you're just measuring the acids.
I put a note in the chat, and Nate's probably going to say something, but anyhow, yeah, people sometimes call it Ripley ratio. It's a great way to monitor. I'll send the lab procedure in so you can see what it is to titrate, how they do it. And then there's also machines. I think I have specs for a machine, if that's an option. Yeah, it's really good.
Luckily here we're using a synthetic substrate, so we kind of know what's going in. It's not like, oh, what's going on with the kitchen today or whatever. So you could maybe even do that one time, and then from there your calcs are a lot easier.
Thanks for that. Actually, I'll follow up on those resources. I will say one of the limitations we didn't talk about is going to be financial constraints and time constraints. So this project is facing a lot. I mean, the world right now, but this project is certainly facing some pressures in terms of operating capacity. And that will limit potentially our monitoring of the extent of which we can get our samples processed. So, I mean, just in response to that, there will be potentially more unknowns than we'd like, because just limitations on labor and procurement. But we are excited and we'll do our best. I do have to run now, but I really love everyone's input, and I'm glad to have gotten FaceTime with everybody. If Margaret collects any more feedback, I'm sure we'll talk again soon and make some plans to get this up and running. And I hope that we'll be able to give you an update once we're at launch. So thanks, y'all. And Wolfgang, it was great to meet you and hear about your project. So we'll have to keep track of that too.
Same to you, yeah.
Thanks so much, Ann. Really appreciate it. I'm gonna have to take off too, but this is really great, and Wolfgang, you're basically doing what we're trying to do up at Gorakshep in the upper Nepal, in the mountains, you know, but we have like a stone building with these big cavities, and then we're insulating that with like bags full of ripped up plastic trash. Like our architect was like, no, we're gonna use the stuff on site. And so like that just kind of lives there forever. And it's like a big greenhouse wall with, you know, there's like windows and things, but we have to have electrical heating, we have to have battery. Like that's you know, more than a third of the cost would just be the electrical system alone and getting it there by helicopter. And there's so many, everything else is going to come by yak or human. And so, but I love to see your like the simplicity of it. And also our colleague, Dr. Jaime, who was not able to come here, he's done this for several of these sort of the climbers' huts in the upper Andes. And so he has some really great case studies where they've done that. And again, it's seasonal, you know, it's kind of freezing and stuff like this. So he's an excellent resource for you to reach out in the next stages of your research.
Oh, nice to hear that there are also other colleagues which facing the same challenges we are for sure doing.
Yeah,
I'll send you a couple of the papers.
Thank you very much.
I have to take off. So nice. But
Yep.
yeah, if I make it out to Switzerland, I'm gonna come harass you.
Yeah,
So.
for sure. Or probably then later we have other projects. So
okay.
Just
yeah,
come.
thank you so much. Okay.
Yeah.
Take care.
Thanks. Take care, Nate. So we don't have anything else that I know of on the agenda, but except like sharing of current projects anyone's got that they want to talk about. Judith?
Hi, sorry I'm late
Hi.
today. I'm in Laval University now in Quebec. I just arrived last week, so I'm still a little bit overwhelmed with the paperwork. But yeah, the project is epidemiology, wastewater-based epidemiology. So in communities in the north of Quebec, in Nunavik, that don't have piping for the wastewater. So they've developed already a sampling tool that's going to be put on the trucks that pump out the wastewater and dump it in a lagoon somewhere. And so we're going there probably in June to discuss the routine and how often they're going to test which trucks, which houses, and so on. And then it's in collaboration with the Ottawa University that will be doing the testing, and the community of Kuujjuaq, and then maybe other communities also will add soon.
I would, for another meeting, maybe be interested in anything that you would like to share on, like we had before. I'm not sure if you were here. We had a presentation from somebody about how they do sanitation in Greenland. Like, I would love to see, you know, what you see. What are they doing? What's the setup for all these different social factors?
Was it maybe Pernilla who did the presentation on that? Yeah. Okay. Cool. Yeah, I'll definitely work on that. Actually, I'm presenting a few times in the coming weeks, so hopefully I'll have something ready for next time.
Good.
Yeah. But I mean, mainly for now, you just have a reservoir, like oh God, how do you call that? Like a big container under the house, and then everything just is dumped in there and then trucked out to a lagoon. So it's just dumped into a sort of lake, and then they have 3 lakes, 1 year each, and then it just drains from one to the next. And the 3rd year it's drained out into the landscape. And just yesterday I asked them, have we tested how efficient that is? And they don't seem to have the results, but we might do that this summer. Take the water that comes out in the first one and out the last one, and see if there's any change for the better, ideally.
And like what? Check for fecal indicator bacteria?
I guess, yeah, mainly.
I have a fun paper. We had some lab work done on the effectiveness of digesters for destroying pathogens and fecal indicator bacteria. There was one that was, all of them were knocked down like pretty much right away, except for one. And I don't know if it applies to you. This would have been manure, maybe manure and food waste. I don't know. I can send you the paper. It's kind of up your alley.
That'd be great. We're planning to go late June this year to the community.
Can I ask, is it stored through the winter and then collected in the spring, or is there a wintertime collection?
I don't know the exact dates, but it seems to be that there's in this community, there's 3,000 people. They have 7 trucks that are constantly going around.
Oh, okay.
So I guess the tanks are not very big. Yeah.
Yeah, that would be a good one for another meeting where your EPA and Alaska people are there, Margaret. Like they could see you. That would be pretty cool.
Yeah.
Although it doesn't necessarily have a lot to do with digesters, but we got to know this stuff. How does it actually work? And ditto, like the climbing huts. Wolfgang, like Nate talked about, Mount Everest. You must have the same issue in Switzerland, right? Climber huts.
Yeah, for sure. Yeah.
And I think I'm not sure if that was one of your potential applications. It was fun to see the alpine dairies as one of your potential applications.
Yeah,
that's a
dairies or the
that's a lot of
Alpine
waste.
Yeah, and the Alpine Inns also, because normally they have kitchens there to cook for the people, so they have residues somehow. They have to deal with this. And let's say what's a big challenge also for them is to get, let's say for heating, let's say for example, like propane or butane, like up there, normally they use helicopters to get the energy there. So it's also a big thing to get all the energy there. So it's not so easy, and probably it's then easier to compensate with something else that we don't need this helicopter energy. Yeah. The question is just what we're doing later on with the digestate, which is left when they're just rocks.
Yep.
So, yeah.
All right. Any other burning questions, desires? Thank you, Judith. All right. That's a wrap. Thanks, everyone.
Yeah, nice to see you.
Bye-bye.
It was